I'm John Massey, Director of Systems Technology at Silicon Graphics. We're here today to take a look in the crystal ball about the future. And for everybody, I see one thing in the future, and that is big data. Future is big data. What does that mean? If you remember nothing else from this series, remember 4x every 3 years. That is, DRAM memory chips and the size of disks goes up 4x every 3 years. That's 16x every 6 years. Either you learn to manage it, move it, address it, control it, or else you're in for a lot of trouble. So let's just take a look at what those growth curves really mean. On this slide, I've got two ways to show the same data. On the left, I've got a logarithmic scale in powers of 10. You can see how fast this goes up. It goes up quite fast. Now, on a linear scale, it looks like it's going faster. It's the nice exponential growth curve. And my friends in marketing like me to use these, particularly when we're ahead of the competition. Unfortunately, it's very hard to show wide ranges of numbers on this kind of chart. So I will use the conservative engineering style and use logarithmic charts in many parts of this talk. So here's the key part of the data. On the left, we've got the number of bits per DRAM memory chip. As you can see, it's been going up at 4x every 3 years for many, many years. Above that, we see the number of gigabytes in a 3.5-inch disk. Disks used to increase at 2x every 3 years. Around 1989, they started going in parallel with DRAM memory. As we'll talk about later, we find that somewhere in 1994 is when microprocessors really needed to get to be 64-bit to be able to conveniently address this data. We'll talk about that in more detail later. Now, let's take a look at what happens to people and organizations that have a great deal of data. We have people who use the computers. They're hooked together with an intranet. They have certain kinds of disconnects that can cause them trouble. The first one is that they have the data, but they cannot understand it. They've got lots of numbers. That doesn't do them much good. A second disconnect is they have an idea in their head, or they have information in the outside world, and there's no sensible way to turn it into data in the computers. So that's disconnect number 2. Number 3 is a really critical problem. Here, you simply cannot have the data, period. There's not enough processing capacity or disk capacity or I/O performance to have the data where it needs to be. This, of course, is the kind that gets you fired. If you tell your boss to stop growing the size of the business because the computers can't keep up, this is well known to be a career-limiting move. Don't do this. The fourth one is a more subtle one. Here you have the data, but it's no longer in the correct place. So it's either on the wrong computer or it's part of a complicated computer, but it's not hooked up in the right place, and it takes too long to get it to the right place. Now, the left half of this chart you might call visual computing. That's what a lot of our desktop machines do. The right half of the chart here is about large server machines and very fast networking to be able to move the data around. You have to handle both parts, and in fact, in our company, about half is on the left and half is here in the middle. Well, the trouble is moving data is input-output, and input-output has a very sad history. We have several quotes here from the past. Seymour Cray, I/O has certainly been lagging in the last decade. 10 years later, Dave Cook said I/O needs a lot of work. 10 years after that, famous computer architects say that I/O has been the orphan of computer architecture, but its revenge is at hand. This is a problem. And it's not a very well-known problem. It's not as obvious as slow CPUs, but it's a big problem. So let's see what a problem this is. On this chart, we've got gigabytes per second going vertically on a logarithmic scale, and we have years going horizontally. 4x every 3 years is the blue line going up. This is the growth of data. Now, the individual I/O channels in computers, unfortunately, have not been growing to keep pace. That's in the green here at the bottom. These are on the order of 1/10 to 2/10 of a gigabyte per second. They're not even growing at 2x every 3 years. They're growing less than that. That is a real problem. The next problem is that if you look at the typical symmetric multiprocessor and you look at its internal bus, its memory, or its total I/O performance, Right now, that's in the range of half a gigabyte to 2.5 gigabytes a second. It is definitely only growing at 2x every 3 years, and it's getting much harder. As you can see, there was good growth from the 80s to the 90s, and that growth has been slowing down. So the problem is the big data gap, which is in between the performance you get from standard machines and the rate of growth in the data. What this means is that you can have the data, but you can't move it around at the speed that it's growing. So we have to do something about this problem. So what is the plan to do something? Well, what we are doing is looking at individual I/O channels, which again are not growing very fast. Being on this trend line and being a little early is not good enough. What one needs is a breakthrough, like something that goes a gigabyte a second or more, and in fact we are doing that, and you'll hear about that later as we announce new products. Now, let's take a view of the world that tells you whether you look ahead to handle this big data flow or not. These are models of two kinds of companies. One kind of company is driven by commodity kinds of systems. A PC company would fit this. They're driven very much by high unit volume and by lowering costs. Taking out even $50 of cost can maybe increase their unit volume a lot, and so that's what they worry about. They do not go too far up in price or performance or configuration because that's not the nature of that business. Also, the business model for such companies is to have a few percent in research and development, but no more because it's a commodity. You can't afford to do more. Now that, of course, is not the kind of company that Silicon Graphics is. Silicon Graphics is much more of a vertical company where it worries about a huge range of functionality and performance, starting down in the middle of the personal computer space and going up to the largest, most powerful computers that are made on this planet. We have to worry about all the things you need to do to make that work. In our case, we worry about reaching the peaks in three different areas: big visualization or big graphics, big compute power, and big data. Not all customers do all three. Almost everybody does big data, and that's why we invented this talk. What often happens is that we try something out at the very high end, and over time the costs naturally come down. We work some of the ideas that started in supercomputers all the way down into the personal computer space. In particular, with the recent merger with Cray Research, we have added larger peaks in both big compute and in big data. Big visualization was already a Silicon Graphics specialty, and in fact Silicon Graphics was active in these other areas. Cray has extended our abilities in these areas. Of course, at the bottom we still overlap with the personal computer space, and that's okay. We bring our own special ideas to this space. Now let's take a look at how these two different companies act when it comes to looking ahead to the future. What we have here is looking at the future, the N generation, the N plus first generation, and the N plus second generation. We all know that every couple years things get faster and better at every part of the price space. The viewpoint, though, is very different between a commodity company and a performance and functionality company. Commodity companies are heavily driven by the past 10 years. There are so many products out there that the installed base limits you in what you can do. All you have to do to see this is go into a computer store and find out how many input-output cards were designed 10 or 15 years ago. There are quite a few. Now, a vertical company does a lot of engineering, and it has to look ahead at least one, sometimes nearly two generations. The result is that this kind of company has to think ahead quite a bit. And I'll give you some examples from the past that show how this has happened and what kinds of effects the two different viewpoints can have on customers. So let's take a look at anticipating the future or not. A good example would be the OpenGL language designed here at Silicon Graphics, which hides a lot of differences between hardware that lets us cover 1,000-to-1 or more range of performance at the same time, but also has been brilliant in anticipating future hardware developments, hiding the differences so that people can use the same software that they have had for years. I really consider this one of the most elegant software designs I've ever seen. I certainly had nothing to do with it, but the people who have done it did a great job. Let's try not anticipating the future. This is where every couple years you change the programming model for graphics. It's at too low a level. All the programs know what's going on inside the hardware. When the new hardware comes, it either has to bring along all of the baggage from the past or everybody has to change. And this seems to go on, in fact, every couple years in the commodity space. Now let's try another good thing to do, and that is to anticipate the I/O needs to include graphics. So we have always done that here. We have often put more I/O performance in our machines than you would expect, simply because we have to feed these voracious graphics units. Let's try not anticipating the future. Around 1994, the PCI bus in the PC space was described as being an incredible leap, enough for everybody for a long time. It's about 100 megabytes a second. Well, that actually is about the same speed as the original Silicon Graphics Indigo that was delivered many years ago. We already went to something twice as fast 3 or 4 years ago because it wasn't fast enough. So in 1996, what we're hearing is, well, PCI isn't quite good enough. Let's do this thing called AGP, the Advanced Graphics Port. And it turns out Microsoft has a completely different view of this called Talisman that they want everybody to do. And the programming models are actually going to end up being different. And this is going to be fairly exciting for the people who build software for a living. So let's try another one. A good thing to do is to ship 64-bit hardware in 1992 and make sure there's a very smooth transition from 32 to 64-bit hardware. As we'll see in the next section of this talk, if you don't do that, you have big trouble. Well, perhaps not anticipating is seeing an advertisement just 2 months ago. Intel wants test pilots for the 32-bit revolution push the envelope. I'm an old computer guy. I thought 32-bit happened at least 10 or 15 years ago, but who am I to say that this is true? Clearly, Intel believes that the 32-bit transition is happening right now. Actually, we thought the 64-bit transition was happening now, but they have a different view. So, the future is big data. Again, if you remember nothing else, remember 4x every 3 years. It's coming. No one ever has too much disk or memory. They always find ways to fill it up. If you don't figure out how to move it, address it, manage it, what you're in for is big trouble, and we'll see that in the next session. So why do I say there's big trouble? Though there's a very major transition in progress in computing. That's from 32-bit computing to 64-bit computing. Some vendors are already very far along with this. Others still have a very large mountain to climb, and frankly, they have big trouble. Let's take a look at that. A few analysts have already started to notice this effect. D.H. Brown and Associates, for example, observes there is indeed a very large mountain to climb for some of the vendors. If you like, you can also read about this in some past history, a 64-bit computing article in Byte magazine over 5 years ago, or databases on RISC and 64-bit just published a few months ago. So there's a few references if you want some background. I'm in a few minutes going to try to explain what the problems are, in particular the subtle problems that are ahead for some vendors. So this is our good old slide of 4x every 3 years. Shows that disks and DRAM memory continue to grow. They grow at this rate, and people want to buy their storage and have it in their machines. No one ever has too much disk or memory, so people keep buying it. Now the problem is that around 1994 we crossed a major barrier. That is, 32 bits used to be enough to address the size of physical memory that people could actually afford in a moderate-sized machine, like a refrigerator-sized server machine. The problem is, by 1994, 1995, you needed more bits than 32 to address the memory you actually could purchase. So this is the point where you really want to have 64-bit computers. Some of us did. What happens when you don't? Well, in the history of computing, every time you could purchase memory but not be able to use it because the programming model wouldn't let you access it, it's been very painful. Let me give you some history from the past. In the 1960s, of course, one of the most famous computers of all time was the IBM System 360. It used 24-bit addressing, which gave 16 megabytes of memory, an unheard of amount of memory at the time. Well, of course, by now many machines are much bigger. They had to expand memory to go to 31 bits. That was the best that they could do. It's still not enough, but it shows what happens when you don't plan ahead a little bit. Then later on, another famous computer, the PDP-11s, came out. These really were 16-bit machines, so you could buy several megabytes of memory, but you could only address 64 kilobytes at any one time. I used to do databases on this kind of machine, and it was pretty exciting because you spent all of your time slicing and dicing code and data to fit into these 64 byte pieces. So not only did the mainframe people do it, then the mini-computer people did it, but then the microprocessor people came along and did the same thing. So when the Intel 286s and 8086s came out, you were often forced into these 64 kilobyte segments. Then DOS came out and put the 640 kilobyte limit on, which people lived with for many years. This was very unfortunate. People made all kinds of strange programming acts to get around this, but they were stuck with it. These illustrate what happens to you if you're not careful and don't think ahead. Now, since the late 80s, it's been obvious, if you look at the kind of charts that I've just showed you, that you would need 64-bit computers by the middle of the 1990s. In fact, at MIPS Computer Systems, we started designing the chips that would be 64-bit. We started that in 1988. Somewhat amusingly, aided and abetted by two other companies, Silicon Graphics and Digital Equipment. A funny coincidence. Now, why do people want to go to 64-bit? Well, there's two separate kinds of reasons. One is for performance. 64-bit can move data sometimes twice as fast as 32-bit, and people use this. People also apply it, interestingly, to cryptography applications. Now, at one point, I might have thought that would be limited to the National Security Agency. It turns out that people doing communications routers actually use the higher performance of the 64-bit chips. And in fact, we actually see 64-bit chips in video games and communications routers and other fairly low-cost products. So this is not something that's strange, that's limited to supercomputers. It actually gets down to $300 or less products. It's already out there. Now, the more strong reason is perhaps for addressing huge amounts of memory. In particular, large physical memories, virtual addressing in machines often adds a couple more bits because you don't have to have all of your virtual memory actually in the computer at once. Now, the technical market will instantly expand to fit whatever their budgets can allow. They're used to having 64-bit clean code because they're used to supercomputers. They often have Fortran programs that they can rework in an afternoon to use whatever memory you can get. We sometimes, in 1995, sold machines with 8 or 16 billion bytes of main memory, and they used it up the next day. So the technical market started wanting this in 1994 or 1995. We've actually shipped quite a few computers that take advantage of this fact. Now, the commercial market needs a little more time because they have very large suites of code, often written in the C language. It takes some conversion and cleanup to make it useful in a 64-bit environment. However, this is a very large market because the key portion of the market that cares about 64-bit are things like relational databases, major key item in the commercial market. Why do they care? Well, the problem is that while disks get 4x bigger every 3 years, they don't get 4x faster every 3 years. The latency or access time to disk uses physical motion, and as a result, it is not improving that fast. The only way the database vendors know to keep improving their performance in the face of 4x every 3 years storage is to get more of that data in memory, or at least the pointers to the data, so they don't have to go to disk multiple times just to find the data. Databases are already very complicated. They do not want to go through what I did in the decades past of chopping things into pieces just in order to have the data. What people want to do is simply buy a few gigabytes of memory, or 4 gigabytes or 8 gigabytes, and allocate 4, 6, or more gigabytes of it directly to the database manager to keep all of the frequently used pointers and frequently used tables. Again, if you look at that Unix review article that I mentioned, it discusses this in some detail. It's very important. All of the major relational database vendors have ports underway to re-architect their code to really make use of 64-bit. So this is very important. Now let's take a look at what it takes to get to 64-bit. Everybody in this business has started with 32-bit software running on 32-bit hardware. The next step you tend to take is that you produce 64-bit hardware, but you run 32-bit software on it because you have to have the hardware to debug 64-bit software, and it doesn't come overnight. The next step is that you either run 64-bit software that only does 64-bit, of course on 64-bit hardware, or you go to a model where 64 and 32-bit are equally well supported, even though it's on 64-bit hardware. The first of those two, 64 on 64, is what Digital Equipment did with its Unix. The second, 64/32 on 64, is what Silicon Graphics did, and which in fact is expected to be the path that other major vendors will take. Now, you may have a few machines in your line that can do this. Later on, you extend this across your product line, and even later at the very top, there are new kinds of machines coming that desperately need to be 64-bit that will require terrible workarounds to try to do with 32-bit chips. We'll talk about that in another session. So these are a couple of the paths to 64-bit. In the Digital Equipment side, their Unix is 64 on 64. Their VMS is a 64-32 mixture on 64-bit hardware. In their case, Windows NT is still entirely 32-bit, even running on 64-bit hardware. Now let's see what other people have to do. The first crew along will be Sun Microsystems. It has been shipping 64-bit hardware for a while. However, it's a few years off from 64-bit software. Hewlett-Packard has just started shipping 64-bit hardware. I believe it will be 1997 before they get any 64-bit software. IBM has discussed a number of 64-bit chips. They've had some problems getting them out. It's unclear when they will actually come out with them, so they're really not even on the first step yet. Now, of course, what makes this very confusing is the combination of Hewlett-Packard and Intel into the IA64 architecture, Merced is what some people call it, that comes out in late 1997 or 1998. Think of this as the Grand Architecture Canyon. They have to leap across this canyon, fill it up in order to be able to move up the mountain. So they have a fair amount of work ahead of them. In fact, this is subtle work. It's only when you plot out the charts of what it takes people to make things happen that you see how complicated this can get. And we'll go through that because it is not obvious to understand. So let's take a look. You're going to see quite a few charts of this form. Along the bottom you see years. Going up you see different vendors. And what we do is go through the transitions for each vendor. So for instance, DEC made a major transition to alphas. That's what the little red star means, is that they really made a major change of architecture, which of course caused a lot of trouble with their customers. They immediately went to the blue, which is 64 on 64. It made for a difficult transition, but they at least were ready for the vertical bar that means this is when you really need 64 bits. Now Silicon Graphics did it a little bit differently, is that we started shipping 64-bit hardware in 1992, and in fact by the end of 1992 we were shipping no more 32-bit hardware. It took us a while to get operating systems to all work, but by late 1994 we were shipping 64-bit operating systems on top of 64-bit hardware. We have then further spread that across the product line. Now Sun is at this point shipping 64-bit hardware, but they're running a 32-bit operating system on that. In 1998, according to their public roadmaps that they've given, they will actually have a full 64-bit operating system. That is, of course, 3 or 4 years later than when people started to want it. It's hard to tell what IBM is doing with PowerPC because the original 64-bit chips were supposed to be out several years ago. We assume that in a couple years they will actually get this out. Now, Hewlett-Packard is in the middle of an especially exciting transition. Clearly, they had once planned to make the same kind of transition as we did. That is, convert over to 64-bit chips, ship 32-bit software on it, fill up their installed base with 64-bit hardware, and then shift all their users to that. Now, so that's the kind of transition they were planning. They've started to ship chips that are 64-bit, still running 32-bit software. Next year, they say they will offer a 64-bit operating system that will still run 32-bit programs as well. Now, of course, they are going to then shortly shift to the IA64 architecture, which is a little confusing for people who buy a machine next year. We'll come back to that. Finally, the HP or Intel architecture that's 64 bits probably appears in 1998, and one will guess either it will run 32-bit software or it will run 64-bit operating system and supports both 64 and 32. Now, of course, Intel is still continuing to build x86 architecture chips, and according to their plans, they're going to build those as well for many years. The IA64 chips will also run those same binaries. But it appears that Intel will have 32-bit chips through the end of the decade and probably longer. Well, it's more complicated than that. That was already complicated enough. Let's see the next issue. You have to actually get applications on systems. Now, different vendors have done this different ways. Digital required people to convert their 32-bit code to 64-bit code, whether there was any particular value in doing this or not. So this meant it took quite a while for there to get to be many applications. In fact, even though systems appeared in 1992, it seemed in practice that it was 1994 or 1995 before most of the important applications got moved over, because it took actual change to the source code for people. That's hard work. Now, Silicon Graphics came out much faster in that we didn't need to convert every single program. We still ran all the 32-bit programs. So we had a very quick transition towards the end of 1994. In particular, our first products were for the supercomputer market here. Those people had 64-bit code, quickly converted it, and in fact, when the machines actually shipped in September of that year, there already were many applications already tuned and very suitable for that market. This is a nice thing about being a player in the supercomputer market, is that people move very fast and they try things out early. Now, we don't know really what Sun and IBM and HP are going to do about getting applications. This is why I have the question marks up there. Most of those companies do not participate in the supercomputer market where people move pretty quickly. So as a result, it may well take them longer than it did for digital equipment, and certainly longer than it did for Silicon Graphics. Now let's take a look at the way hardware ships in companies. No one makes an instant cut to 64 bits for everything. After all, even digital equipment was still shipping MIPS and VAX-based machines. At least for digital, every single alpha is 64-bit because it was a brand new architecture. In Silicon Graphics, as shown by the little purple triangle, during 1992, we not only shipped our first 64-bit product, but we shipped our last 32-bit product. Think of the purple as 32-bit only hardware. Sun Spark has started to ship 64-bit hardware, but it is still actively shipping 32-bit hardware almost a year after the 64-bit chips. That's because the 64-bit chip they have only fits the mid-range and higher products. It does not fit their low end, so they are actively shipping new 32-bit hardware. Why is that important? Well, people do expect that you will support hardware you ship for some number of years. They are not happy if something they bought last year is instantly obsolete. So as a result, if you are still shipping 32-bit hardware, you will be supporting that for at least 3 to 5 years. Hewlett-Packard has the same situation. Perhaps they will do it faster, perhaps they won't. My bet is they will still be shipping 32-bit HP precision architecture chips in certainly 1997 and probably into 1998. Now, HPIA chips are entirely 64-bit underneath. Intel x86s are entirely 32-bit. What does that mean for installed base? Well, we'll look at that at the next slide. Now you see how the installed base converts, and those are these longer triangles coming to the right. Just because you are shipping 100% 64-bit systems doesn't mean that your installed base is suddenly converted. People do not upgrade their systems or change them out overnight. So, in our case, we stopped shipping 32-bit hardware at the end of 1992. By the end of 1994, beginning of 1995, as shown by the little square, we did our last operating system that supported the 32-bit only type hardware. Now, that meant that people got another year or two of life out of those machines, but that was the last time that we made sure something would work on the 32-bit only hardware. And I believe this is fairly typical of the industry, is that you don't have new operating systems for hardware forever, simply because 4X every 3 comes after you, and you rapidly get new products that are so much faster than old ones that you want to use the new capabilities. Now for Sun, I believe that their installed base will still have large numbers of 32-bit systems at least until the year 2000 or perhaps later. And if they follow the same pattern, around the year 2000, they probably will ship their last 32-bit only operating system. PowerPC will take even longer. Their roadmaps show active shipment of 32-bit only chips well beyond the year 2000. So my guess is they will have a long time before they get much converted to 64-bit. Hewlett-Packard has a sort of similar situation. I have to guess from their announced plans that they still will need to support existing 32-bit hardware through at least the year 2000. Now, why does that matter? One thing is that software vendors look at this kind of chart and wonder what it is that they have to do, because they care about selling to the installed base. They also care about selling on the new products. It takes a long time to convert installed base. That's why we started early, did a very quick transition at Silicon Graphics, because we knew it would be years before the installed base really got converted over to 64-bit. So there is always this lag between shipments and when the installed base converts. Hence, when you see advertisements for 64-bit, you ought to ask a vendor, so what fraction of your installed base is actually 64-bit capable? In our case, when we shipped 64-bit operating systems that covered the product line, we were able to go and put that on systems that shipped in 1993. Now, this next slide shows how complicated it can get if you're not careful. And I don't mean to pick on Hewlett-Packard and Intel, but they have an exceptionally complex transition coming up, and I'm sorry it led to a complicated slide. So let's take a look at what they are going to need to do in the next few years. Right now, they have Hewlett-Packard Unix on a 32-bit processor, PA7000. That's the first operating system. The second one they have is HPUX on a 64-bit processor, PA8000. That will end up being a second operating system as it learns how to take advantage of 64 bits. When they switch to the IA64 architecture, they will have to emulate, that's 1E and 2E, both of those existing binaries on the new machine. This, by the way, is not an easy emulation. They have to convert the code to fit the new machine. Well, now they're also going to want native versions of their operating systems on those new machines, because you lose performance otherwise. What it appears is that they will have one operating system that can run either of two kinds of binaries. Now, why would you have two kinds of binaries? Well, to get to the actual 64-bit capabilities, you would want a new native binary on the IA64 architecture. On the other hand, many programs frankly have no reason to ever convert to 64-bit. You would want to also get their performance, though, on the machines, and they would want to compile in 32-bit mode. Now, is that complicated? Yeah, that's complicated. There's a lot of flavors of things. It's going to be fairly exciting for third-party software vendors. It's going to be fairly exciting for customers because they've got to keep different combinations of these actually working all together. It's really exciting for operating system software developers because to keep sanity in the marketplace, you have to synchronize your software releases across a number of different platforms. And that's always harder work than just producing one operating system. By the way, HP, in its most recent release, has exactly one operating system that runs on their machines. Now they're going to have 2 or 3 operating systems and 4 different flavors of binaries. This is just for Unix. They also support another operating system, MPE, and they're going to have to do the same thing. So let's look at the pass-through here. You can start with a 32-bit binary and run it forward. If you want to get 64 bits on PA8000s, you'll do some code conversion. If you want to run that binary up on the new machines, you'll have to go do emulation. That's sort of done automatically for you, but it's going to lose some performance. If you start with a 32-bit binary, you could keep it and then go to emulation up on the new IA64 machines. Observation is the pink square here shows a time that, to me, it doesn't make much sense to buy PA RISC machines. If I were buying, I think I'd want to hold off because they're just about to obsolete this with the new IA64 machines. The green larger square here indicates a period that is really going to stretch the support resources, even of a large company like Hewlett-Packard. So this is hard work. It's a lot of effort. It's a lot of extra coordination. It means it's more difficult to get operating system releases out. It means there's many more opportunities for bugs. I guess I'm sensitive to this because I'm really an old operating system guy. I've been through transitions, not quite as fierce as this, but I've been through exciting ones, and it gives you gray hair very quickly. So let's look at the other side, which is Intel. It's a little simpler, but not too much. And the Unix side, they have 32-bit operating systems running on x86 chips. That's the first operating system. What they're going to want to do is emulate that code on the new chips. They have a lot of hardware to help do that. That should actually perform pretty well. It may well be that people just compile code for the x86s for a long time. They're going to have to do that because Intel will be selling x86 chips for quite a few years, as shown at the very top. On the other hand, they are going to want to take advantage of the new chip architectures, which are supposed to be better. So they will have a new native Unix operating system, which presumably will support the libraries and code for both 32 and 64-bit at the same time. So they're going to have at least 2 operating systems. And again, this is only for Unix. Windows NT is going to have to go through a similar set of transitions and have similar numbers of binaries floating around. Now, if we compare the previous slide and this, you might say, well, why don't they combine and only have one of these sets of binaries? Well, there is this minor problem that the byte ordering on Hewlett-Packard machines is what's called big endian. The byte ordering on Intel is the opposite order, which is little endian. So in fact, these things that look like they might be the same programs actually are not. There's 2 separate binaries they have to worry about. So this is hard work. Now let's take a few lessons from all of this. The first lesson is that you ought to shift the hardware first, get the installed base converted over. Then it's pretty reasonable to shift the software without cutting off your customers at their knees. The second thing is, no matter how much you like to talk about new technology, responsible vendors have to support their customers for many years. They need to support the installed base of hardware with new operating system releases for probably at least 3 to 5 years. The installed base thus takes years and years to move, especially if it's a large installed base. Anytime customers and software vendors have multiple choices, it gets confusing. If I have to compile a program, which version of all these things do I compile? Well, I can compile one version that will run across many machines, but it will lose performance. It certainly is the case that when, for instance, computing spec benchmarks or similar industry standards, people will want to cite the numbers for the new native architectures, even if most programs are actually never compiled that way. It's also the case that the support burden on a computer vendor can easily multiply to a huge extent. Not only do you need more people to support the additional flavors, But there's this subtle problem of having to coordinate the release dates so that sensible things happen when a customer has a mixture of them. So the bottom line is that if you do a careful plan ahead, and I've talked about this in the past, about companies that really think ahead about technology. If you do this carefully, you can make a smooth transition for your customers. If you don't do a careful plan ahead, you've got a big transition and you've got really big trouble coming. That completes my discussion of big data, big trouble. In others in this series, we'll look at the big solutions to some of the big problems that our customers have out there. We have some new architectures, some new kinds of computers that will help people solve all these big problems that are coming at them.